Hello, hello. Good evening, everyone. So I guess we'll get started right away. I think this is about everyone we're expecting. So let me just share my screen real quick. Cool. Can everyone see my screen? Just checking. Yeah, just say in the chat if you can't share the screen, if you can't see the screen. Okay, I'll take that as a yes. Okay. So welcome everyone to the first number theory tutorial for MindNZ. So yeah, this is going to be our first number theory tutorial, and I believe we'll have about six or so over the next coming months. So yeah, just a bit of a quick self-introduction then. So I think I'm moving the thing. It's not good. All right, cool. Hello everyone. So my name is Alston Yam. I am currently a year 13 student in high school, and I go to Maclean's College, which is pretty cool. And yeah, in my spare time, I like to play music. So I play percussion, specifically like drum kit, and I also play some other stuff, which is pretty cool. I'm trying to learn some new instruments as well, but I'm getting there. And here's my email address if everyone can see. So alston.yam@gmail.com. If we have any questions basically throughout the month, stuff like that, you're welcome to just email me with any questions. I'm always happy to answer. Or if you are to write up some solutions to any problems that we have in the class, feel free to email them to me. I'm happy to provide feedback. I think that'll be good. Okay, so let's just have a look at what we're going to be going over today. So we'll be talking about modular arithmetic and also inverses, which is pretty cool. Here we see we'll first go over some notation first, and then we'll see specifically how we do modular arithmetic, and then we'll move on to inverses. These two topics are actually quite interrelated, so I believe it's gonna flow pretty well. Okay, notation. Let's start with some definitions. So, okay, first thing I'm gonna introduce to everyone is this triple equal sign. So, the triple equal sign, if I switch over to my whiteboard, all right, just checking. I think my whiteboard's bugging a little bit. 1 second, guys. Let me refresh the page, see if that helps. Yay. Okay. Cool. Everyone can see the whiteboard, right? Okay. So the first notation I would like to introduce is this triple equal sign that we have over here. So on my slide, I've written A is this triple equal sign, which we will call congruence. So A is congruent to B mod N. That is our first notation. So the congruent sign here is actually quite similar to equals, except it's not exactly equals. So I'll explain why. I'll explain how. So we can say that under mod n, A is congruent to B. And this will be exactly the same as saying, what's happening? N divides A minus B. So the difference between A minus B is divisible by n. That will be exactly the same as saying A is congruent to B mod n. So that'll be kind of our first definition. Um, we might notice that here it actually means that A and B will leave the same remainder when you divide it by n. So it will be A and B leaves the same remainder when divided by n. And that's pretty cool, right? As you'll see later on, there will be a lot of useful properties basically that we can use with this notation. So let's start with the first thing, and that is if we have A is equal to P times N plus R. So essentially we've used the division algorithm, which is we've taken as many N's as we can out of A, and then we have some remainder left over. This is just the same as saying A is congruent to R mod N, right? Because while A and R, they will leave the same remainder when we divide it by N. Okay, so this gives us a cool way to relate numbers to the remainders. And yeah, that's what we have on the slide here. And then you might notice that under mod n, there are only really n possible values that we can have. And that is from this set over here. So we have 0, 1, 2, all the way to n minus 1. Well, if something is congruent to 0 mod n, that will mean that that number is exactly divisible by n, right? So if we have A is congruent to 0 mod n, well, then that means from our definition before, oops, let me move my stuff. From our definition before, we have n can divide A minus 0. Well, that is just the same as A, right? So we have A, n divides A. So when we say something is divisible by n, we can basically write it as A is congruent to 0 mod n. And the n possible values that we can obtain under this mod n, we call them residue classes. So residue classes is basically the name we give to the possible values we can have under mod n. Okay, cool. Let's go on to some properties. Yeah, this is essentially what I've said earlier. We have if A is P times N plus R, then we can say that A is congruent to R mod N, and then, yeah, that's what we had before. So remainder will be in the set 0, 1, 2, all those n minus 1, and then by convention, we'll put the remainder on the right-hand side. Yeah, and there are also a lot of interesting arithmetic that we can do with mods. So that is the modular arithmetic part that we'll go on later today. So before we do that, then I think we have some exercises or problems. I think about 2 minutes just for everyone to kind of have a go at the problems, and then we'll go back in 2 minutes and we can discuss them. Cool. Oh yeah, if you have any questions at any point during the lecture, if I'm going too fast, stuff like that, you can either just unmute yourself, let me know, or you can text me in the chat. I'll keep an eye on the chat as well. Okay. All right, cool. I think that's about enough time for just these two exercises, right? I think these are pretty basic. They are just a little exercise based on what we've just went through. So if we go over to the whiteboard, we have 51 is congruent to what? Mod 4. Well, basically, this is just asking us what is the remainder when we divide 51 by 4, right? So let's try to write 51 as a multiple of 4 plus a remainder. So what would be the nearest multiple of 4 that is to 51? That is also less than 51 because we would like the remainder to be positive at this point. Maybe if we have time, we'll go over some cases where if the remainder is negative, what do we do? So, well, 51, we can write it as 4 times 12 plus 3, right? Because we know 4 times 12, that's 48. 48 plus 3 will give us 51. And underneath mod 4, the 4 times 12, well, it kind of just vanishes, right? Because when we are taking mod 4, we're dividing stuff by 4. We're taking the remainder. So this entire section with 4 times 12, well, that will leave a remainder of 0. So we don't really need to care about that. So actually, the remainder of 51 when you divide it by 4 will be equal to 3. So in our case, we'll have 51 is congruent to 3 mod 4. Cool. 51 will be congruent to 3 mod 4, and that is our answer for basically our first question. And then let's move on to the next one. So let me scroll down. 81 is congruent to what? Mod 7. We can do this basically exactly the same way. So, well, let's see what is the remainder of 81 when we divide it by 7. I think we can see that pretty coincidentally. I don't think I intended this when I made the question, but when we divide 81 by 7, the answer, the quotient we get is actually also 12. So 89, when we divide it by 7, we will have 12, and then remainder will be 5, right? Because we can write 89 as 7 times 12 plus 5. And 7 times 12, we can check that this is 84, and we plus 5, that'll be 89. So that is all good. Cool. And like what we said before, under mod 7, the 7 times 12 itself just vanishes, and then we're left with a remainder of 5. So in this case, we can say that 89 will be congruent to 5 mod 7. Well, we can see that in our case, we have the 3 mod 4 here. We also have the 5 mod 7 here. Well, what we can notice is that the 3 here and the 5 here, they're both smaller, right? They're both smaller than the mod. So the 3 is smaller than 4 in mod 4, and the 5 is smaller than 7 in mod 7. That is basically the same as what we said before, how we have the remainder has to be in the set 0, 1, 2, all the way to n minus 1. Because, well, if we think that the remainder can be anything above n, anything larger than n, we can take another n away. And it will reduce it down to a number in the set from 0, 1, 2, all the way to n. And then, yeah. Okay, that is just some basic notation we have for mods. Let's go on to the more interesting part, and that is modular arithmetic. So we'll be doing arithmetic. And when we think of arithmetic, I think the most common thing I would think about is the following. So we have addition, subtraction, multiplication, division, and exponentiation, which is just repeated multiplication, as I'm sure we all know. We can actually do basically all of these under mod arithmetic, but you've noticed I have put exclamation marks next to division because in division, in modular arithmetic, doing division is slightly different compared to how we normally do division. But otherwise, most of it will remain exactly the same. So let's just go over these real quick. So we have first thing, addition and subtraction. So underneath mod arithmetic, we can basically do addition and subtraction. So if we have a look at this bullet point here is if we have A is congruent to B mod n and C is congruent to D mod n, then we can essentially add the two. So we can add the A and the C, put it on the left, and now will be congruent to B and D, and we put it on the right. So yeah, if we add the two numbers, the remainder when we divide it by n will also add. And I think I'll go on to prove this fact. So let's go back to the whiteboard and we can see that A congruent to B mod n and C congruent to D mod n. And we would like to say that in this case, the result of A plus C will be exactly the same as B plus D mod n. Well, let's give it a proof. Okay, let's prove this fact. And what I'm going to do is I'll go back to the definitions. So because we know A and B are just some random integers that happen to have the same remainder when we divide it by n, let's write it as just that using the division algorithm, right? We can have A is equal to, notice the equal sign here instead of the congruent, instead of the 3 dashes, I will use our normal equal sign. So A is equal to, let's call it K1 plus R1. So the K1 and the R1 are integers, right? We can write A as some multiple of n and I'll plus its remainder. And in a similar way, let's write B as K2n plus R1. Notice how I wrote R1 here and not R2, but I wrote K2 here. And this is actually because we have the condition here. So we have the condition here that A is congruent to B mod n. And we can do this because we can see that both A and B will leave a remainder of R1 when we divide it by n, right? Because when we divide by n, the K1n disappears, the K2n also disappears. So we will have A is congruent to B mod n. That is the same as writing it like this. And in a similar way, we can write C is equal to some K3 and so some other integer. It doesn't have to be the same integer over and over again. Like, yeah, C doesn't have to be, it doesn't have to be K1 or K2. And we also have R2 in this case, right? C is equal to K3n plus R2. Because what we have here is we only have C is congruent to D mod n, but we don't know if C is congruent to A or B. So the C congruent to D mod n, we can translate that into our normal, basically our normal arithmetic, and we have D is K4n plus R2. Cool. Yeah, so we have four numbers A, B, C, D, and we've written them in terms of a multiple of n, and we will plus it with its remainder. So what do we want to prove? We want to prove that A plus C, when we divide it by n, will leave the same remainder as B plus D. So let's do that. Well, we know that we have values, we have our representation of A and C, right? So let's write let's just compute what A plus C is. So A plus C, that will equal to K1, K1n plus R1, and we will plus that with C, which is K3n plus, what's happening? K3n plus R2, right? Because we've just used our assumption from before. So A plus C, and we can also basically take out the brackets and we can factor out the n, right? Because we see that the K1n and the K3n, they both have a factor of n. So we can do it like this. K1n plus K3n plus R1 plus R2. And we can factor that as n times K1 plus K3 plus the remainder, which is R1 plus R2. Okay. So A plus C, we have written it in this form, and then we've converted it after we added it. After we've added A and C, we have converted it into essentially a multiple of n over here, and we will plus its remainder. And just like how we've done mod n before with our other numbers, with our 51 mod 4 and 89 mod 7, we can ignore the k, or ignore the n times k1 plus k3 thing under mod n, right? Because under mod n, this thing kind of just disappears, and that's pretty cool. So if we write this under mod notation, we will actually have A plus C is congruent to R1 plus R2 mod n. So A plus C is congruent to R1 plus R2 mod n. And in a similar way, let's look at B plus D. So let's have a look at B plus D. So B plus D is equal to K2 n plus R1 plus K4 n plus R2. I am just substituting this term and this term into this equation. Okay, let's do the same thing as before. So K2n plus K4n plus R1 plus R2. That'll be our rearranged, essentially, equation, and that would be equal to n times K2 plus K4 plus R1 plus R2. And just as we've done before, we can ignore the n times K2 plus K4 term because this is, after all, a multiple of n. And we can also say that B plus D will be congruent to R1 plus R2 under mod n, because we have just computed this thing over here with our representation B and D. So what we notice here is that we have R1 plus R2, and we also have R1 plus R2. So that's pretty cool. We have just proved that A plus C will be congruent to R1 plus R2, and that will also be congruent. That will also be congruent to B plus D mod n. Happy days, right? A plus C is congruent to B plus D mod n, and let's box that in because that is our first result in modular arithmetic, and that is addition will behave exactly the same as our normal operations under mod n. Okay, let's go back. So addition and subtraction, Subtraction is actually surprisingly similar to addition. In fact, it's basically exactly the same because subtraction, we can just think about subtraction as adding a negative number. And if our proof before of why a plus c is congruent to b plus d mod n will hold exactly the same if we were to do subtraction. Specifically, if we have a is congruent to negative b mod n, well, then we have, let's go back to the whiteboard. Okay. Let's do a heading of subtraction. Cool. Let's assume we have a is congruent to negative b mod n. And we also have c is congruent to, let's make it d mod n for now. Whoops, what's happened? B mod n. Cool. What we can do is we can do a plus c will be congruent to negative b plus d mod n, right? And that will also be congruent to d minus b mod n. Because, well, we can switch the order of our addition subtraction and it wouldn't change the result. So yeah, that's pretty much how we do negative numbers in mod arithmetic, really. So we have a plus c. If we assume a is congruent to negative b mod n and d mod n, we will have a plus c is congruent to negative b plus d, which is d minus b mod n. Cool. Yeah, that's basically the same idea as addition that we've just kind of moved on to subtraction. And let's go on to the other operations, which is multiplication and exponentiation. Exponentiation, which is repeated multiplication, right? Okay. I think I will leave this as an exercise. So for an exercise, let's have about 5 minutes to think about this problem, and then I will prove this. Specifically, if we have A is congruent to B mod n, and C is congruent to D mod n, then we can multiply, basically we can multiply the two corresponding terms, which is A and C. We can multiply A and C together, and that will be congruent to B multiplied by D. So AC is congruent to BD under mod n. Well, if we have proved this, then we know that we can multiply something inside mod n, and the remainder will also be kept the same as when its remainders multiply together. So we have let's take about 5 minutes to have to think about this, and I'll come back and I'll prove this effect. And yeah, as always, if you have any questions, just send them in the chat and I'll try my best to answer them. Okay, cool. I think it's been about 5 minutes. So let's go back and try and prove this fact, basically. Cool. Let's go back to the whiteboard. So what we have here is A is congruent to B mod n, C is congruent to D mod n, and we want to prove this statement over here. So let's see how we can do this, right? I think a good point to start is, well, is actually do exactly as what we've done previously here. Because we already have information about A and B, C and D. So the information to before is, well, exactly the same. It's just that the result we're trying to prove is slightly different. So I think a good point of attack to this problem is let's start with writing the same assumptions. Right. So let's start with writing the same assumptions. So we have A is equal to K1n plus R1. B is equal to K2n plus R1. C is K3n plus R2, and D is K4n plus R2. Cool. This is exactly what we had before. So, well, what do we do in the previous question? We've subbed in the values for A and C, and we computed A plus C, right? So let's do the same thing here. And let's compute A times C. So A times C is equal to K1n plus R1, and I'll multiply it by K3n plus R2. Okay, that's cool. And let's try and expand our brackets. Right? I think that's good. So to expand our brackets, we can do this times this, and we'll have this times this, right? So we have K1, what's happened? K1n times K3n, and we can add that with K1n, oh my gosh, K1n times R2 plus K3n times R1 plus R1 times R2. Yeah, that's just me expanding these brackets, and let's do a bit of tidying, which is equal to K1, K3 times n squared plus K1 R2 times n plus K3 R1 times n plus R1 times R2. That will be K1, K3 times n squared. And let's factor out the n and the n that we have over here. So we can factor these out, n times K1 R2 plus K3 R1. And we can't really do much with R1 times R2, so we'll just leave it there. Well, what do we notice? So every term, actually, with an n in them, we can just essentially cancel them in our mod n system, right? Because we already know that anything that is a multiple of n, we can kind of cut it off in our mod n system because they were all congruent to zero mod n because they're all exactly divisible by n. So we can get rid of this one and we can get rid of this one because both of these are integers and they are also divisible by n. So we actually have AC is congruent to R1 times R2 under mod n. And that is just getting rid of these and keeping our R1, R2 term because we can't really do much about it. Okay, let's do the same thing to BD, and I'll be quick. Let's do the same thing to BD, which is K2n plus R1 times K4n plus R2. So let's expand this. We have K2, K4n squared plus R1 K4n plus R2 K2n. And we also have a R1 times R2 term at the end to tag along. Yeah, it's the same thing as always. We have all of these terms. They are divisible by n. So when we go under mod n, we have BD is congruent to R1 times R2 mod n. And yeah, essentially we're done here because if we have a look at these two terms, AC is R1 times R2 mod n, BD is R1 times R2 mod n. So these two AC and BD must be the same under mod n. So AC is congruent to BD mod n, and we are done. That is what we wanted to prove, right? Back at the top here. That's what we wanted to prove. Okay, so we've just proved that our properties, our arithmetic properties of multiplication actually holds in modular arithmetic. So if we have two terms that leave the same remainder when we divide it by n, when we multiply them together, the remainders will also multiply under mod n. And that is essentially the same thing as our normal multiplication. And as a corollary, I don't know. Yeah, exponentiation is actually the same thing as multiplication because for this one, we are just repeatedly multiplying the same thing. So if we go back to the whiteboard, we have let's have A is congruent to B mod n again. And we can raise it to some other power. Let's raise it to the C power. So A raised to the C power. That is A times itself, C times. That will be congruent to A times A times A times dot 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 times A. And that will happen C times. Well, that is also congruent to B times B times B dot 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 times B. C times 2, right? Because we have our previous property here. If we just imagine C is also equal to A and B and D is also equal to B, well, then we essentially have A squared is congruent to B squared under mod n. And we can extend that to any power, basically. AC is congruent to A times A times A times itself, C times. That will be congruent to B times B times itself, C times, which will be B to the power of C mod n. And yeah, that means we can basically raise both sides to the same power, and they will be still the same under mod n. Okay. Now, before I go on to division, which is slightly different. So if we go on division, we'll have to introduce a different concept, which is called inverses, which we'll get to. But before that, let's have some quick exercises. So we have 3 exercises over here. I think we can take about 5 minutes or so and just have a look, have a think about these 3 problems, and then I'll come back and go over the solutions. Okay. Okay, guys, whoops. I just realized I've made a typo. So for question 3, if a to the x is 1 mod n, and another condition is that n x is the smallest number, that this is possible. Yeah, apologies, I've made a typo in the slide, but yeah, so we have x actually needs to be the smallest number so that ax is congruent to 1 mod n. Then it'll be true that x must divide y. Yeah. Okay, I think it's about time. I think I've given a little extra time because of that little typo over there. But okay, let's go back to our whiteboard. So I've just copied the questions down here. So our first exercise is that we want to find every integer n that 15 and 7 will leave the same remainder when you divide it by n. So basically, what are the possible values of n such that 15 is congruent to 7 mod n? Well, let's use some of the properties we've discussed just then. I think specifically what I'm going to do is I will use subtraction, right? So I can subtract 7 from both sides, and you'll see why in a second. So I can do 15 minus 7 will be congruent to 0 mod n, right? I've essentially moved the 7 to the other side. I've subtracted 7 from both sides, however you want to think about it. And we know that 15 minus 7 will just be 8. Is congruent is 0 mod n. I've just computed the left-hand side over there, right? Okay, a is congruent to 0 mod n. Well, that's pretty interesting, right? Because if we have a number that is congruent to 0 mod n, that must mean that that number is exactly divisible by n, right? Yeah. So that's pretty cool. So we have 8 is congruent to 0 mod n, which means that n must divide exactly 8. If we are unfamiliar with this notation, so this vertical line notation, it just means divides. So we just have, this is the same as n divides 8. Cool. This vertical line means divides. And well, what we can see is n divides 8. So n must be all the possible divisors of 8, all the numbers that can divide 8. And we know that what the possible divisors are, right? So the divisors of 8 are actually just 1. Oh gosh. 1, 2, 4, and 8. 1, 2, 4, and 8 are the possible numbers that actually divide into 8. And we can go back and check. I claim that n equals 1, 2, 4, and 8 are the only answers in this problem. So we can go back and check, right? Obviously, if we are taking under mod 1, so if we're taking n mod 15 is congruent to 7 mod 1, then both of these are divisible by 1, right? Any number when you divide it by 1 is always divisible. So n is equal to 1, obviously that will work. And if we go to n equals 2, we know that both sides leave a remainder of 1. Both sides leave a remainder of 1 when you divide it by 2, so that will also work. 4, we see that the right-hand side 7 is congruent to 3 mod 4 because it leaves a remainder of 3. And 15 here, it leaves also a remainder of 3 because 15 is 12 plus 3, right? 12 plus 3, and 12 is divisible by 4. So under mod 4, both sides will be congruent to 3 mod 4. That will also work. And finally, for 8, we know that 7 is already less than 8, so we don't really have to do anything about it. And 15, when we divide it by 8, will leave a remainder of 7. So both sides will be 7 mod 8, and that will also work, which is pretty cool. I think from this problem, right, it is very easy to basically miss cases if we were just to go by the trial and error route. Because I think the first thing that I see when I see this problem is I immediately notice that 2 has to be a solution, right? Because we know that both sides are odd. But as often with Math Olympiad, what you see at first is not everything, right? There are often solutions. In this case, 3 other solutions that you would have missed if you only saw that both sides are odd. So what we've just talked about, our subtraction, where we can subtract the same number from both sides. That will help us find all the solutions. So yeah. So for this problem, we will have found all the possible solutions. Okay, let's move on to the next problem then. So in the original problem, I've worded it as what is the remainder when we have 3 to the power of 100 and you divide it by 7. Well, that is exactly the same as saying what is 3 to the 100 congruent to under mod 7. Cool. So let's have a look at that. Obviously, it will be really tedious if you were to actually compute 3 to the 100 because that is a really, really large number, and I don't think anyone have the time to do that. So let's see what we can do then. So even though I just said we can't compute 3 to the 3 to the 100, let's still try our hands on some small cases and see where that gets us, right? Because I think it's always nice to do some small cases beforehand. So we can have 3 to the 1 is congruent to 3 mod 7. I am just looking at essentially what would happen if I were to change the exponent of the 3, because the 100 is pretty arbitrary, right? If I wanted to, I could go up to like 1,000, 10,000. It wouldn't affect it that much because 100 seems pretty random. So let's just see what happens when I change the exponent. So 3 to the 1 is congruent to 3 because we know that is just that will just be 3, right? 3 to the 1 is just 3. 3 to the 2 then. 3 to the 2 is congruent to 9, but that is also congruent to 2 mod 7. Cool. That is congruent to 2 mod 7. Now, what I'm going to do is I will use our multiplication property. So we saw before that if we multiply, multiplication is preserved under mod n, right? So what I can do here is I can multiply both sides by 3. So if I multiply both sides by 3, the congruence will still be true. So if I multiply the left by 3, that will become 3, let me just move over, 3 to the power of 3. And that will be congruent to 2 times 3, which is congruent to 6 mod 7, right? That will be congruent to 6 mod 7. Okay, let's actually keep going because what I want to do is I want to get to a specific number. And that will make everything a lot easier once I get to that number. And you'll see later on. Cool. Let's go to the next line. Let's multiply both sides by 3 again. And we can change the indices. Change the number at the top of 3. So let's multiply both sides by 3. We have 3 to the 4 is congruent to 6 times 3. And that is 18. And we can compute that that will be congruent to 4 mod 7. Right? Because 18 is 14 plus 4, and 14 is a multiple of 7. Let's keep going. 3 to the 5 is congruent to 4 times 3, which is congruent to 12, which is 5 mod 7. And we are still not at the number, the magical number that I'm hoping for. So we'll do one more iteration, which is 3 to the 6 will be congruent to 5. Whoops, it's a really bad 5. 5, what's happening? 5 times 3, which is congruent to 15, and that will be congruent to 1. Whoops, I think I am not showing it at all. So over here, 3 to the 6 is congruent to 3 times 5, which is 15, which is 1 mod 7. All right, because we know that 15 is 14 plus 1. And aha, that's the magical number I'm looking for, right? Why is 1 mod 7 so special? Well, we have the property that 1 to the power of anything, right? 1 to the power of anything is always 1, which is pretty cool. And we also know that exponentiation is preserved under mod whatever. It doesn't matter what the mod is. Exponentiation is always preserved. So we have, let's just write it down here. 3 to the 6 is congruent to 1 mod 7. Well, okay, now I can kind of do exponentiation now, right? Because the right-hand side will always stay the same. So what if I raise it? Let's try to raise it to the 2 power. So let's raise it to the second power. So we are squaring both sides. That will mean 3 to the power of 6 squared is congruent to 1 squared mod 7. Let's look at what the left-hand side is. The left-hand side, 3 to the power of 6 squared, that will be equal to 3 to the power of 12, right? If we look at our exponent rules. So 3 to the power of 12 is 1 mod 7. I have just squared the 1 here, which is 1. Cool, let's keep doing that. Actually, what I'll do is I will multiply both sides by 3 to the 6. That way it'll be easier to see the pattern, right? So if we do 3 to the 6, so we have 3 to the power of 12 times 3 to the power of 6 is congruent to 1 times 3 to the power of 6, which is our multiplication property. And that will be congruent to 1 mod 7, right? because 3 to the 6, we already knew that it is 1 mod 7. So actually on the left, we have 3 to the 18 is congruent to 1 mod 7. That's pretty cool. Because if you see the pattern, we have 3 to the 6 is 1 mod 7, 3 to the 12 is 1 mod 7, 3 to the 18 is 1 mod 7. So you might guess, well, what if all the multiples of 6 are actually 1 mod 7, right? If all the multiples of 6 on the exponent are 1 mod 7, well, then kind of we can get really, really close to 3 to the 100. Well, specifically, what is the nearest multiple of 6 that is less than 100? I would think it is, let me think, it would be 96, right? Because we know 96 is divisible by 6. Just as a side note, 96 divided by 6 will be equal to 16. Cool. So what I can actually do, I should not have written this problem so close. Let's see. Yeah, I'll erase this one out to get more space, and I'll write it later. Okay, 19 divided by 6 is 16. So 96 divided by 6 is 16. So 96 is a multiple of 6. What we can do is we can do 3 to the power of 6, and we know that is congruent to 1. I will multiply, or I'll exponent both sides to the power of 16. Right? Because if I take the power of 16, as we know, exponentiation still keeps the same mod properties. So 3 to the 6, and our exponent to the power of 6 will be congruent to 1 to the power of 16 mod 7. Well, wait, that's pretty cool, because on the left, we have 3 to the power of 96, and that's already really, really close to 100, right? And on the right, we have 1 mod 7. Okay. Well, we are only a power of 4 away from 100, aren't we? So we can take 3 to the 96, and we'll multiply 3 to the 4 to both sides. That'll be congruent to 3 to the 4. And well, wait, we've already calculated what 3 to the 4 is. 3 to the 4 is right over here, right? 3 to the 4 is congruent to 4 mod 7. So we can actually write it down here. So 3 to the 4 is congruent to 4 mod 7. And well, if we look on the left here, 3 to the 96 will, oops, I think my AirPods died. It's not very good. Can everyone still hear me all right? I think my AirPods just died a little bit. If you can't hear me, just text me in the chat. Okay, cool. Yeah, on the left, we have 3 to the 96, and we'll multiply it by 3 to the 4. So here we actually just have 3 to the 100. And that was what we wanted, right? We wanted to find 3 to the power of 100 under mod 7, and we found that, and that is 4. So we can say that 3 to the power of 100 will leave a remainder of 4 when we divide it by 7. Okay, that's pretty cool. If we think back at what we've done, so the whole bit over here at the start was just us trying to find the pattern, right? And we wanted this golden number of 1 because we know that we can kind of keep stacking the ones. We can keep raising both sides to the power of something, and the 1 wouldn't change. And that's really cool because we wanted something like that so we can get really, really close to that big 100. And through that, we kind of found that all 3 to the power of a multiple of 6, because we know that 3 to the 6 is congruent to 1 mod 7. But then we have 3 to the power of everything that is a multiple of 6 is also congruent to 1 mod 7. And what we've done is we've kept multiplying 3 to the power of 6s until we got to 96. And we got to 96 and we got really close to 100, and then we can just say, well, I'm already this close. Let's multiply 3 to the 4th and actually get to 100. And we've just done that, right? Actually, from this problem, we can see that the 100 actually really doesn't really matter. We can change it with 1,000, 9,000, 7,000, I don't really know. And it wouldn't really affect it that much because we know that all 3 to the power of something, and if that something is a multiple of 6, we have that. It'll always be congruent to 1 mod 7, and we can just multiply whatever we want to make it up to that number we actually need. And we will find the remainder under mod 7. Okay, let's go to the third problem, which is if we have a, oops, let's do this. If we have a to the x is congruent to 1 mod n, and we have a to the y is congruent to 1 mod n, and we also have x is less than y, and x is the smallest number that is possible. X is the smallest number that is possible such that a to the x is 1. Well, this problem actually is kind of similar to the one we just did, right? If we have a look over here, we found that in this case, n is 7 and a is 3, if we just kind of match what we have. And x is actually equal to 6 because we have looked through all of the possible values that 3 to the something can have. And we found that the smallest number to give a remainder of 1 is actually 6. So x will be equal to 6 in this case. And here, if we have any a to the power of anything, and that is congruent to 1 mod n, we already know that, well, 6 will divide anything, 3 to the power of anything. That gives a remainder of 1 when we divide it by 7. So in our case, in our special case where a is 3 and n is 7, we've kind of already proven it, right? So we are just trying to generalize this idea. We're trying to see if we can extend that to any a and any n. So we want to prove x divides y. I think with this one, what we've actually done is already plenty to solve the problem, right? We can just kind of modify our logic a little bit. So if we have a to the x is congruent to 1 mod n, let's try and let's just keep multiplying a to both sides. So if we multiply 1a to both sides, we have a to the x plus 1 is congruent to a mod n. Okay, let's keep going because we know that, oops. Let's keep going because we know that y is bigger than x, right? And we want to try to get it up, get the index of a up to the number y. And then we'll try to find what the remainder is. Let's keep going. X plus 2 will be congruent to a to the 2 mod n. And if we keep going, a to the x plus x. So when I have multiplied both sides by a to the x, well, now here something really interesting happens because on the right-hand side, we have a to the x, and that will be congruent to 1 mod n by our assumption right over here, by our condition. So the left-hand side is a to the 2x, the right-hand side is 1. And any number, whoops, any number in this bit that I circled here, okay, maybe except this one. Let me just recircle. So any number in this bit will actually not be congruent to 1 mod n, right? That was the typo I made before. So any number in this red circled area. So a to the 1, a to the 2, a to the 3, all the way to a to the x minus 1, any number here, they will not be congruent to 1 mod n because we have assumed that x is actually the smallest number to do so. Okay. So we have a to the 2x is congruent to 1 mod n. Cool. That's cool. We can keep going. If we multiply both sides by a to the x again, we have a to the 3x. It's congruent to 1 mod n. I'm just going a little faster because we kind of already have the idea, right? If we keep multiplying a to the x's, eventually we will hit y, right? Why is that? Because precisely why I have circled these numbers over here, because we know that these numbers do not give a remainder of 1 when we divide it by n. So the only numbers that will give a remainder of 1 when we take mod n will be multiples of x. And if the only numbers that will give a remainder of 1 when we divide it by n is multiples of x, then we have that since a to the y is one of these numbers, we have y must be a multiple of x, and we are done with the question. Is everybody happy? Okay. Yeah, as I've said, if you have any questions, send it in the chat, or I have there's the email. There's my email at the start. Feel free to email me and I'll try to answer. Okay, let's move on to our last bit of stuff, which is division under mod arithmetic. Division is actually tricky because you can't always do division in mod, right? Whereas in before, we can just add numbers, subtract numbers, multiply numbers, raise some numbers with exponent. It's always we can always do that. But for division, it's a little different because if we have a look, right? We have 6 is congruent to 0 mod 3. That's a given, right? Because 6 is divisible by 3. But then if we divide both sides by 3, on the left-hand side here, we have 6 divides 3. 6 divided by 3 is 2, but on the right, we have 0. But 2 is not congruent to 0 mod 3, right? So clearly something must have gone wrong when we try to divide 3 on both sides. So let's have a look at why and what's happened, right? To deal with divisions, we need to introduce one final thing, and that is inverses. Now, inverses are pretty cool in mod arithmetic because they are a really powerful result. And that is if we have a as an integer and n is a positive integer, so we have essentially what we had before, and then we call x an inverse of a modulo n. That is a new term that might be unfamiliar to some of you. So x is the inverse of a modulo n if we have a times x is congruent to 1 mod n. So if we have some number and then we times its inverse, that will give us 1 under mod n. Like basically what I did with the previous example of 3 to the power of something, the 1 is pretty special in mod arithmetic. But they don't always exist. And to see that, let's go back to the whiteboard. I will just copy down the definition. So we have x is the inverse of a modulo n if a times x is congruent to 1 mod n. Okay. It is quite hard to think about this in any kind of general n, in terms of any general n. So let's look at some special cases. And the first special case I'll have a look at is what if n equals p and p is a prime? We know that primes in number theory is pretty special. They have a lot of cool properties. So let's have a look at why. Let's have a look at what happens when n is actually a prime. Cool. We will consider the following. So we'll have a set of 1, 2, 3, 4, all the way to p minus 1. So we have p minus 1 numbers over here, and that's a set. And let's consider the set. And we have our integer a before, right? And I'll also construct another set, which is all of these. So 1, 2, 3, 4, all the way to p minus 1, and I'll multiply a to all of these. So we'll have a, 2a, 3a, dot, 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 all the way to p minus 1, a. So we have two sets of numbers. One is just 1, 2, 3, 4, all the way to p minus 1, and the other one is all of these numbers multiplied by a, where a is our number before. The key claim that I'll make is that every number in here will, okay, I'll rephrase this. The key claim I'll make is this set over here is a permutation of the first set. Well, what does that mean? It just means that, whoops, every number in the second set will be equal to exactly one number in the first set. So let's take a. So a, if we take it under mod p, a will be congruent to something, right? I don't know what that is just yet. Okay. A will be congruent to, let's call it B1 for now. Under mod P, because A has a remainder when we divide it by P. 2A will be congruent to a different number, B2 mod P. 3A will be congruent to some number B3 mod P. And then we keep going to P minus 1 times A will be congruent to BP minus 1 mod P. Okay, so we have P minus 1 numbers of B here, right? So we have B1, B2, B3, all the way to P, B of P minus 1. And the claim is that all of these numbers, so all of the numbers that I have circled here, they make up the set 1, 2, 3, 4, all the way to P minus 1. So I'm just saying that there's exactly one number in here that is equal to 1, exactly one number in here that is equal to 2, exactly one number in here that's equal to 3, etc. The proof of this, I'll just go over right now. And after that, we can have a look at inverses, basically the properties of inverses. So let's go and have a proof. And we will prove this by contradiction. We will prove the claim that both sets are a permutation of each other. So we'll go by contradiction. So suppose that we have an I and a J they are called indexes of the numbers in the second set. So if we have ij is congruent, ia is congruent to ja under mod p. So if we have two numbers in the second set that are actually the same under mod p, well, if that was true, then my claim will be wrong, right? So because how contradiction works is that I will start with a false claim, arrive at a contradiction, and I will prove that the thing I claimed was actually wrong. So the result that I wanted to prove is in fact correct. So we have ij, and we suppose, for the sake of contradiction, that ia is congruent to ja mod p. If we prove that this is wrong, well, then what that means is that there will not be any I and j in the set that are the same under mod p. And if all of these are different and there are p minus 1, numbers in the set, and all of them are different, then it must be that they make up the set, right? Because they also have p minus 1 numbers, and they're also all different. So we have a bunch of different numbers in here, exactly p minus 1 of them, and they will make up the set. So if we prove that this cannot happen, then we will be done. Okay, so let's go about and prove that. So ij is congruent, ia is congruent to ja under mod p. Let's use our subtraction property from before. So let's subtract ja from both sides. We can do ia, and I'll subtract ja. And that'll be congruent to 0 mod p. That is from our assumption. And we can factor the left-hand side, right? We can factor a out, and we'll have a times I minus j will be congruent to 0 mod p. Cool. Cool. That's what we have here. And remember what we had before, our assumption, our notation, right? If we have a times I minus j is congruent to 0 mod p, this actually means that p will divide exactly a minus j, right? Because a times I minus j is congruent to 0 mod p, p will divide this. Cool. And when p divides this, and we know that p is a prime, that was why we kind of supposed the fact that n was a prime. We know that it must be that p divides a or p divides I minus j because p is a prime. And our assumption for this case over here is that a is coprime to p. Okay, a is coprime to p. So this case will not happen because p cannot divide a. So therefore we must have p divides I minus j, and we can write that back in mod term, which is I minus j is congruent to 0 mod p. If it's congruent to 0 mod p, we have I will be congruent to j mod p. So essentially what we've done is we have deducted from this assumption. So this assumption that IA is congruent to JA mod P, we have deducted. We have deduced the fact that I will be congruent to J mod P. Okay, well, that is pretty bad. Why is that pretty bad? Well, if I and J are actually congruent on the mod P, that actually means I and J will have to be the same, right? Because what are I and J? I and j are just the numbers 1, 2, 3, all the way to p minus 1, because remember, ia and ij are numbers in the set. So all of these 1, 2, 3, all the way to p minus 1, they're less than p. So for them to have the same remainder when we divide it by p, it must be that they are the same. But that is a contradiction because, well, if they are the same, then they are trivially true, and we have, so if I and j are the same, then I and j are the same number, but we have assumed that I and j were different numbers and they were the same under mod p. Okay, so that is incorrect, right? So our assumption that there are some ij such that ia and j are congruent under mod p is incorrect. So actually, every number here will be different under mod p. And specifically, every number here, so one of these B1, B2, B3s will be 1. Well, that's important, right? Let's go down. We know that exactly one of B1, B2, B3, to BP minus 1 will be equal to 1. Okay, that's pretty cool. So let's pick out the number that when we multiply it by A gives a value of 1, right? So we can pick out, say, I. Oops, let's call bi equals 1, and that is the only number out of the B sequence that is equal to 1. So we can take IA is congruent to BI, and that will be congruent to 1 mod P. And would you look at that? So IA, our I here, is actually our inverse of A. So we've multiplied A by some number, and we got the 1, right? We got this magical 1 underneath mod P. So what we have proved is that A here, if it's in mod P, where P is a prime, we have proved that IA, there exists an I such that IA is congruent to 1 mod P. So I will write it as a result here. If P is a prime and A is a integer coprime to P, then there exists an integer I such that IA is congruent to 1 mod P. And we will call this I the inverse of A. Whoops. We'll call I the inverse of A. So essentially what we have proved is that if P is a prime, and we have any number that's coprime to P, that number will always, always, always have an inverse. But that is not the case for if the number we're taking the mod as is not a prime, right? So if we go back to our slideshow, let's think about it this way. If we go back to our slideshow and we had this example over here, 6 is congruent to 0 mod 3, but that does not mean 6 divided 3 is congruent to 0 divided 3. Why is that? Well, we have divided. Now we know we have divided by 3 here. And that's pretty bad, right? Because 3 is the mod we're taking. So anything when we multiply by 3 will always be 0 mod 3. So this actually doesn't really make sense to be doing this, because the number we are dividing is not coprime to the prime 3. Okay. Cool. That is one of our key results. So an inverse will always exist when we are taking under mod P, and our A is an integer that is coprime to P. We can actually extend P to any n, given that A will satisfy some conditions. Okay. I think we are approaching the end hour of our lecture. It is 8:30 over here. So I think I will leave this as an exercise to the reader. So let's have a think about how the behavior of A will change when we change P from a prime to any positive integer. And I believe on the PDF that I've written, I think there is, I believe, an exercise that talks about just that. So yeah. I think that's about it from me for today. We can have a look at the problems I've put on the PDF, and if you would like, you can attempt some of these problems and feel free to email them back to me. So once again, that's my email over here, alston.yam@gmail.com. If you would like to attempt some of these, write up some solutions and send them to me. That will be great. And I'll be happy to give some feedback. So yeah, that's about it for me for today. Does anyone have any questions? I think I will stop sharing. Cool. Right, that's about it. Thank you everyone for coming, and I think I'll see you in about a month or so for our next session. Yeah. Bye everyone. Yeah, I think I'll stay here if anyone has any questions and stuff. Where did I buy my drum kit? It's actually a drum kit from my friend. So I got my drum kit for free actually. So my friend, they used to play the drums and then they stopped playing the drums and I was like, yo, can I please have your drum kit? And then it's very kind of them. And then they gave it to me. And then I think I bought some like custom drum heads from Rock Shop and I've like slapped them on there and now I use it. It's pretty cool.